As we said before, the cardiovascular system is a system because it includes a series of organs. The heart that pumps blood into circulation, the arteries that carry blood away from the heart, the capillaries which serve as the sites of exchange of nutrients and gases, and the veins that carry blood back towards the heart. Here, we want to specifically look at the capillary portion, the sites of nutrient and gas exchange. We're going to start off with a quick analogy. If we take a look at any lake that's made by damming a river, the river moving into the lake has a noticeable current to it, but the lake itself, because it is much larger and has a larger cross diameter to it, has no perceptible current. On the other side of the dam, where the lake is funneled back into a smaller diameter river again, we start to feel the current again. Our capillary beds are a lot like this kind of structure. Blood flows slowest through the capillary portion of our cardiovascular system. This slow movement allows time for the exchange of gases, nutrients, and waste products. The slow flow is caused by the total cross-section diameter in the capillary bed. Each individual capillary has the smallest diameter of any blood vessel. But if we take a look at the total cross-section of all the capillaries in a capillary bed, their total diameter is massive, far larger than that of even the aorta. Because of that, the arterioles feeding blood into the capillary bed act like the river that's going into the lake. The capillary bed itself acts like the lake. Its total cross-section is so much larger that the movement of fluid is far, far slower. On the other side of that capillary bed, the blood is drained back into a venule that acts like the river draining blood away from the capillary bed, where the current can pick up once again. In the capillary, oxygen, nutrients, wastes, and hormones need to be exchanged between the blood and body tissues. This exchange happens by diffusion down concentration gradients. Because there should be more oxygen and nutrients in the blood, that material diffuses out of the blood towards the body tissues. Because the body tissues have been producing carbon dioxide and nitrogenous wastes, those metabolic waste products should diffuse down their concentration gradient into the blood. However, this diffusion of different types of molecules can be accomplished in a number of different ways. Simple diffusion of lipid-soluble molecules can occur directly through the cells of the tunica intima. Because these molecules are lipid-soluble, they can diffuse directly through the plasma membrane of those cells that make the lining of the capillary. Some small molecules that are not lipid-soluble can diffuse directly through the intercellular capillary clefts, or through those fenestrations like we find in the kidneys. We're using small gaps to allow diffusion of those materials that can't go directly through the plasma membrane. For those things that are large or are not lipid soluble, we need to use active transport to move those across the lining layer of the capillaries. This active transport involves the movement of vesicles shuttling materials between the blood and the interstitial fluids. While those nutrients, gases, and wastes are being transported by diffusion, bulk fluid flow is also happening. Fluid is forced out through the clefts on the arterial end of the capillary bed, and most of that fluid is returned on the venous end. This impacts fluid volumes in both the bloodstream and the interstitial space of the tissues. This bulk fluid flow is caused by two opposing forces, hydrostatic pressure and a colloid osmotic pressure. Hydrostatic pressure is the force blood exerts out on the wall of a capillary. Essentially, it's the same as the blood pressure within that capillary. This outward pressure forces fluids to filter out of the blood and into the interstitial space. Because this fluid is being forced out of the capillary, hydrostatic pressure declines as blood moves towards the venous end of the capillary bed. There's less volume, so there's less pressure on the venous side. The hydrostatic pressure on the arterial end of a capillary bed measures around 35 millimeters of mercury. But on the venous end, that pressure has dropped to about 17 millimeters of mercury. Large non-diffusible molecules, like proteins such as albumin, pull water towards themselves. So this osmotic pressure represents an inward pull of water that opposes the outward pressure of hydrostatic pressure. Because these large molecules don't diffuse out of the blood, osmotic pressure of the blood is nearly the same on the arterial side of the capillary bed as it is on the venous side. This inward osmotic pressure measures about 25 millimeters of mercury on both ends of the capillary bed. So if we take a look at what's happening on the arterial and the venous end, we can start to get an idea of the net filtration pressure. That is the difference between hydrostatic pressure and the colloid osmotic pressure. On the arterial end of a capillary bed, hydrostatic pressure represents 35 millimeters of mercury. That's 35 millimeters of mercury pushing out from the capillary. The osmotic pressure pulling into the capillary measures about 25 to 26 millimeters of mercury. That means that there is about a 10 millimeter difference, or 10 millimeters of mercury difference, causing a net outward movement of fluid on the arterial end. On the venous end, hydrostatic pressure has decreased because fluid has been leaving the blood. So hydrostatic pressure on the venous end measures about 17 millimeters of mercury, whereas osmotic pressure stays about the same as it was on the arterial end, 25 to 26 millimeters of mercury. That means that there is now a greater inward pull than there is an outward push. There's a difference of about 8 millimeters of mercury, causing an inward movement of fluid on the venous end. Now we may notice here that the outward movement on the arterial side is a little bit larger than the inward movement on the venous side. That means that fluid does tend to pool up to a small degree in the interstitial space. Because of that, we need something like a lymphatic system to help us gather this accumulated fluid and return it back to circulation. We'll take a look at that lymphatic system in future videos.